Okay, so the final speaker in this session is Majenz. He's talking about adaptive reprogramming in the QROM.
Thanks, Marco.
Okay, you're unmuted.
Yes. As Marco said, I will be talking about adaptive reprogramming in the quantum random oracle model, and this is joint work with Alex Grilo, Kathrin Hövelmanns, and Andreas Hülsing. Here's an outline. Oops. Sorry. Here's an outline of my talk. I will start with a motivation where I describe the quantum random oracle model and its purpose. Then I will go on to describe a game that I call the adaptive reprogramming game, which is kind of the setting where our results are situated. I will present our results afterwards and say a little bit something about the proof and present an algorithm that we develop to facilitate it. Okay, let's start with the quantum random oracle model. So the quantum random oracle model is an idealized model for cryptographic hash functions. So let's start to talk a little bit about hash functions. So a hash function is a function that maps an arbitrary amount of data to kind of a small fingerprint of that data. And the intuitive security requirement for such a hash function is that if you have the fingerprint and you encounter some data, you should be able to determine whether this data was used to generate the fingerprint or not. This very simple principle has a number of applications in cryptography, for example, including digital signature schemes and message authentication codes, but also for achieving strong security for public key encryption, for commitment schemes, etc., etc. So hash functions are really literally everywhere in cryptography, at least if there's if kind of the settings are sufficiently complicated. Now, the concept of hash functions is very simple, right? I was able to explain to you what a hash function is, at least in rough terms, within a couple of seconds. But it turns out that when we try to use real-world hash functions and their real-world properties to prove security of the applications, then this is oftentimes hard. And one way out that researchers have been taking is the so-called random oracle model, or the quantum random oracle model, when we're in the setting where there's quantum attackers. So this is an idealized model for the hash function, and let me explain to you how this works in detail. So here's a comparison of the random oracle model. Now, just for now, let's restrict to the classical case. So let's talk about the random oracle model. And here's a comparison of it with the real world. So in the real world, a hash function, like for example, SHA-3, is a function. You can look up its definition on the internet. You can implement it on your computer and compute it on any input, right? Now, to model this function, we just pretend that this function was picked uniformly at random from the set of all functions. Now, this, of course, will, with high probability yield a very complicated function, and we can't just hand it to people because it will not have a compact description. So instead, what we do is we provide all agents with black box access to this random function H. And this includes honest protocol participants, but also adversarial agents, right? Because in reality, everybody can compute it. So in the model world, everybody should be able to evaluate it. This has a number of advantages. Like, for example, it leads to simpler proofs of security. And because of that, basically, there are also more efficient constructions with provable security in the random oracle model than there are in general, at least in the standard model without this idealization, right? Now we want to talk about quantum attacks, right? Post-quantum security and also quantum cryptography. Here we always have to assume that attackers have a quantum computer. And if they have a quantum computer, in reality, of course, they can evaluate the hash function on their quantum computer. To account for that, the model world has to be changed as well. So now we have to provide all agents with the ability to perform quantum evaluation of this random function. And this is basically what the quantum random oracle model is about. And this was introduced by Bonnet et al. In 2010. This has a number of consequences. Right now, security reductions are quantum algorithms, even if we talk about classical cryptographic schemes, right, that are attacked by quantum attackers. And we need to resort also to quantum query complexity when we, for example, characterize the hardness of certain tasks relative to these oracles. Now that we know what the quantum random oracle model is, I want to present you the adaptive reprogramming game, which is kind of the setting in which our results are situated. So this is kind of a very simple game. I will present the simplest version of it. There are kind of a little bit more general versions, but I will stick to the simplest version for the sake of the presentation. So in the setting, we have a uniformly random function, right? That makes sense. We want to learn something about the random oracle model or the quantum random oracle model. And let's assume that this function h goes from n bits to n bits. That's just for simplicity. And the game is played by a two-stage algorithm, A. It proceeds as follows. So A starts, the first stage, A0, starts to interact with an oracle for the random function h. After doing this for a bit of time, it will output a state. So this is just an internal state of the algorithm that is passed on to the second stage. Now a bunch of random data is generated, a random bit b, and also random strings x star and y star. And the idea now is to reprogram the oracle h if b is 1 and otherwise leave it untouched. So let's define a version of h that is reprogrammed to output y star on input x star and be unchanged everywhere else. And let's define h0 to be the original function and h1 the reprogrammed version. Now the second stage of the game proceeds by a1 receiving the internal state and x star, the potentially reprogrammed input, as an input. And then it can interact with an oracle for hb. So that is for the original function if b equals 0, and for the reprogrammed version if b equals 1. And finally, A1 is supposed to output a guess for the bit B, which we call B prime. Of course, A now wins this game if B prime is equal to B, right? Okay. It turns out that in the classical setting, this is an extremely simple game. And it's easy to come up with a bound on the advantage of such an algorithm in winning this over random guessing. So here is such a bound. The advantage is upper bounded by a term proportional to the number of queries that the first stage, A0, makes, divided by the domain size of H, right? And this turns out to be tight. They're matching algorithms, and I will talk a little bit more about this later. Now, before moving to the quantum setting, let me talk a little bit about applications of this in post-quantum crypto. There are a number of security proofs for digital signature schemes in the random oracle model that rely on the characterization that I just showed, basically on this lower bound for the number of queries that you need to win this game with significant advantage. And these include hash-based signatures, like, for example, XMSS, which is a stateful hash-based signature scheme that's standardized. But also Fiat-Shamir signatures, which is kind of a class of signature schemes that are constructed in a generic way from a certain class of interactive zero-knowledge proof systems. And in addition, also like a variant of this Fiat-Shamir transformation that I mentioned that guards against so-called hardware, so-called fault injection attacks, which are hardware attacks, et cetera, et cetera. So there are a couple of applications. Now, of course, if we want post-quantum security, so that's security of these classical cryptographic schemes against quantum algorithms, then we need to prove a version of this lower bound that holds when A0 and A1 have quantum access to their oracles, right? Remember that this H here is supposed to model a hash function. So in the quantum setting, we need to provide quantum oracle access. Now, there is a bound readily available that was proven by Unruh in 2014, and it bounds the advantage over random guessing by a term proportional to the number of queries that A0 makes, divided by the square root of the domain size of H. Now, great, of course, that's good. We have a bound, and it's also, it seems to behave fairly well. But of course, what's a bit disappointing is that it does allow for a significant advantage over the classical case. Right now, only 2 to the n½ queries are necessary for constant advantage, while in the classical setting, 2 to the n queries were necessary. And I mean, now we could say, okay, fine, this is the quantum setting. Usually we lose a square root because of Grover's algorithm, right? But if we look a bit closer, it's somehow unclear how Grover's algorithm should be applied here, because A0 really doesn't know where to look, right? I mean, A0 just tries to scrape up as much information about the function h as possible without knowing where to look for the relevant information, which is the output of h on input x star, right? But it doesn't know x star. So somehow there shouldn't be this Grover advantage. This is kind of this was the starting point for our work. So let me move on to present our results. We went back to this problem of characterizing this adaptive reprogramming game in the quantum setting. And here is our theorem. We prove that the advantage of any algorithm A in winning this game over random guessing is bounded by a term proportional to the square root of the classical advantage. So note that this is, does allow for an improvement over classical. So the quantum oracle axis does help. But at least now, again, there are 2 to the n queries necessary for achieving constant advantage. So basically, the query complexity of winning with a constant advantage remains the same as classically. And let me just mention that this is kind of the simplest version of our theorem, as this is kind of the simplest version of the adaptive reprogramming game that I presented here, where you have generalizations for situations where there's several reprogrammings and where the adversary has partial control over the position where to reprogram, so over x star. And these are important in applications. Now, in addition, we also devise an algorithm that that achieves exactly this kind of behavior, right? That has an advantage that's proportional to the square root of the number of queries that A0 makes times 2 to the minus n. Okay, so now that I have presented the results, I can quickly say that kind of a little bit about the impact, right? What this means now is that we have tighter security proofs for post-quantum signatures, including some candidates in the ongoing NIST competition, right? There's this competition for the standardization of post-quantum cryptographic schemes ongoing, and a number of candidate signature schemes use the Fiat-Shamir transformation, for example. And there are some of them, for example, Picnic, that have now a better security proof because of this result. Okay. Let us move on to have a little bit at a look at the techniques that we are using. So the bound that we prove is proved using the so-called superposition oracle technique. So in the next couple of slides, I want to explain to you this technique and how we do reprogramming in this technique. And then I will explain to you a little bit more about how the proof of the lower bound proceeds. So the superposition oracle technique was introduced by Gendry in 2018. And it's kind of a technique of simulating a quantum accessible random oracle in a way that has added benefits for security proofs. Let me explain to you a little bit how it works by comparing it to the kind of vanilla quantum accessible random oracle. So for a random oracle, right, we need a random function. And how is the random function sampled? We can just sample it by sampling a random n-bit string for each input, right? So we sample a random n-bit string at h of x for each input x. Now, in the superposition oracle, what we do instead is that for each input x, we initialize an n-qubit register fx in the uniform superposition of all outputs, right? Basically, we take the uniform superposition of all n-bit strings instead of sampling a random n-bit string. Now, in the random oracle, the query unitary is just the standard way of evaluating a classical function in a unitary way, right? We apply the function to the input register X, and then we XOR the result into the output register Y. Now, in the superposition oracle, what we have to do is we have to use the contents of these registers fx. So how do we do that? What happens is that if the adversarial register X is initialized in some state, some computational basis state X, then what the unitary does is it applies C0 from fx to y. So what does that mean? It means that controlled on the input type register X of the adversary, the contents of fx are kind of coherently copied into the y register or XORed into the y register. So basically what that means is it just does the same as the random oracle, right? Except that it reads h of x from this register fx. Now we want to do reprogramming of such random oracles, right? So how do we reprogram in the classical setting? What we do is we kind of, in some sense, repeat the first step here, right? The initial sampling step for the input to be reprogrammed. So if we want to reprogram at x star, what we do is we sample a random n-bit string y star, and we define the new oracle to, output y star at input x star and remain unchanged elsewhere. Well, kind of the first insight that went into our proof is the following. It's basically that we can do exactly the same strategy in the superposition oracle. We can just reprogram at input x star with a random new fresh random output if we discard the contents of register fx star, and then we prepare it in a fresh, independent, and pure uniform superposition state, right? So there's really a kind of a concrete algorithmic way of reprogramming the superposition oracle. It's almost kind of a physical and concrete way, right? In the standard way of thinking about a random oracle, we think about random variables and so on. But here we think about concrete quantum registers, and we can just, perform some operation to reprogram it. Okay, so having understood this, we can look a bit closer at the proof ideas. So first of all, if we look at this adaptive reprogramming game again, and if we in particular keep also the bounds and the classical bound in mind, then it becomes clear that somehow the number of queries that the first stage makes is the limiting factor, right? Somehow A0 is the algorithm that has to learn as much as possible about the function h without knowing where to look. And A1 just has to pick up the pieces in some sense. So therefore, what we can do is we can just simplify the situation by removing any restrictions on A1. So in particular, we can just allow it as many queries as it wants. And this amounts to essentially giving A1 just the whole function table of HB as an input. Right? So now A1 doesn't have any oracle anymore. It just gets the whole function as an input, which is kind of even better. Now, what we're still missing is kind of a way to get a handle on kind of this the amount of information that A0 learns about H, right? So A0 makes quantum queries to H. We cannot kind of keep track of which inputs are queried, etc. So this is kind of a difficult situation, and that's why we introduced the superposition oracle into the situation. So we now model the random oracle that A0 interacts with as a superposition oracle. So I drew this box here with its registers, and just keep in mind the way that kind of the queries are answered. They are just answered by operating on the adversary's query registers and the oracle registers. Now that's great, but now we kind of can't give A1 the whole function table as an input anymore, right? We have kind of replaced the function by this superposition oracle, but it turns out that we can do something that is even stronger or gives A1 even more power, and that is to just hand A1 the whole internal state of this oracle simulation as an input, right? So now, and this of course happens after potentially reprogramming it. So that's great, because now somehow the whole Oracle distinguishability task for A1 has just been transformed into a state discrimination task, right? A1 gets as input this internal state that might be quantum and these registers from the Oracle. And now it just has to distinguish whether the Oracle was reprogrammed or not. So it has to discriminate between these two cases, which kind of implies two different input states for A1. So that's great, right? Because we know how to do state discrimination. So it just suffices to bound a trace norm distance for arbitrary algorithms A0. And this is how the rest of the proof proceeds. And I will not describe the details of that. Okay, so in the last couple of minutes, let me describe our matching algorithm. Right now we have a bound, but we will also have an algorithm that achieves the advantage allowed by the bound. So let me describe that. To do that, let's go back to the classical situation. So here we have this advantage that's proportional to the number of queries of A0 divided by the domain size of H. So how do we achieve this? There's actually an extremely simple algorithm, right? A0 can just make Q0 arbitrary but distinct queries, store all the outputs at all input-output pairs it has achieved in this way, and pass them on to A1, right? Now A1 just hopes that X star is among the inputs that A0 queried, and if so, it can check whether the output of its oracle is the same as the one it received from A0. Otherwise, it has to guess. And this is exactly achieves the right advantage. Now, there is a bit of an improvement of this algorithm in terms of space usage, right? If you look at the first algorithm, then it really needs a lot of space, right? A0 needs to pass on Q0 inputs and Q0 outputs to A1. Now, an alternative is that A0 generates the inputs in some deterministic way that's known to A1 and XORs all the outputs and passes them on to A1. Now, A1 can just do the same computation and compare these two checksums, right? And if they're the same, then probably the oracle has not been reprogrammed. And if they are different, then it has been reprogrammed. Okay. Now, in the quantum algorithm, we want to achieve this kind of square root advantage in terms of the advantage over random guessing, right? So how do we do that? We want to run the checksum algorithm in superposition over different sets of initial inputs. So to do that, let's adapt the classical algorithm a little bit. Here's the set of n-bit strings. We just pick some cyclic permutation on the set of n-bit strings. And this is now our way how to generate the inputs, right? So we just start with some input x0, and the next input is c of x0, then c squared of x0, et cetera, et cetera. So we repeatedly apply the cyclic permutation to generate the subsequent input. Now what A1 can do instead of checking, it can, in some sense, uncompute this checksum, right? Which is classically completely equivalent. Now here's how the quantum algorithm works. We start with a uniform superposition of initial inputs and an empty output register y. Now we repeatedly apply the oracle to x and y and the cyclic permutation to register x. And now A1, basically receiving the registers x and y, tries to just undo the second step. To analyze the situation, we need to quickly kind of define some sets. So x star is the input that possibly has been reprogrammed. And now let's just go back Q0 steps along the cycle here and define the set of inputs obtained or passed along in that manner as S. Now it turns out that, of course, if the oracle has not been reprogrammed, we get the state phi 0 back. But if it has been reprogrammed, then we get the state phi 1, which I show here in the bottom. And it's just a superposition where basis states in the set S are paired up with a computational basis state that's different from 0 with high probability. Basically, the old output at x star, XOR the new output at x star, and every other input is paired up with the 0. So there, basically, the uncomputation has succeeded. Now, there's two more insights that go into the algorithm. First of all, A1 has a description of the state phi 1. because it has X star as an input, so it can and it knows the permutation C, so it can compute the set S, and in the end, it kind of has a description of the state. So actually, it can perform the discriminating measurement between phi0 and phi1. And phi0 and phi1 are quite far apart. Their distance is basically proportional to the square root of q0 times 2 to the minus n. Okay, so that's great. Now, the only thing that's left is to perform this measurement. And it turns out that this is actually possible efficiently in polynomial time in the number of queries Q0. Okay, this brings me to the end of my talk. I have shown you a tight characterization of the so-called adaptive reprogramming setting in the quantum setting, right? And this informs the NIST competition for post-quantum crypto schemes in that it provides tighter proofs for certain schemes that had kind of non-tight proofs before. The proof is based on the simplest version of Genry's superposition oracle, and I also showed you how you can achieve the bound using an efficient algorithm. Thanks a lot.
Okay, thanks a lot for your talk. I'm still watching the Slack channel for any questions. So far we have none. So mine is actually a bit about, well, more about the application of your results. So you said it informs this NIST competition. As far as I understand, they're kind of in the final round of selection. Did any of them actually improve their parameters because of your result? Do you know?
Yes, that's. I mean, somehow these kind of provable security plays more of a supportive role in this kind of concrete crypto world, because usually parameters are chosen based on cryptanalysis, basically based on the best known, they are kind of optimistically chosen, but based on the best known attacks instead of basing it on the best known proofs. It can, of course, if you have like comparable schemes, right, that have comparable security, then the one with better provable security maybe is to be preferred.
Okay, but I mean, it cannot be, okay, the best known quantum algorithm, I guess that's what they're comparing to. Okay.
I mean, they are doing both, right? I mean, somehow the best known classical algorithm is also very important because, I mean, if we expect to deploy these schemes before quantum attacks are feasible. So yeah, you know, to actually be prepared. And at that point, we are very interested in the classical, best known classical attacks against these schemes. That's actually one of the main concerns. But of course, the purpose of this is post-quantum security, so another interest are kind of quantum attacks.
Yes, but your results don't, I mean, would they also give a potential attack, improve a potential attack?
I'm not so sure about that, because somehow the algorithm that I presented, right, that kind of wins this adaptive reprogramming game. I mean, it can be used to show the tightness of our bound, but in the concrete situation, we have a concrete hash functions, right? So basically, it's much more likely that there's an attack that's based on the fact that the output of this hash function is in fact not random, but it's some concrete function, then on that it's based on some algorithm that uses kind of the re-randomization of this imaginary randomness. So I don't think that our algorithm concretely can lead to an attack. But the bound itself, which is kind of the best, we showed that it's the best one that is possible for this situation, and that just gives kind of an improved confidence about post-quantum security for some schemes like Picnic.
Okay, yeah, thanks a lot. So I see no further questions, then well, thank you again.